When you look up at the night sky, among countless stars, you'll notice a few brighter points of light. Those are the planets in our solar system. However, you won't see the most common types of planets in the Milky Way, super-Earths and mini-Neptunes. These planets are larger than Earth but smaller than Neptune, accounting for about 1/3 of all discovered exoplanets. However, they do not exist in our solar system. Why they don't appear around the Sun is a tough question that astronomers are currently racking their brains to answer. To unravel this mystery, astronomers need to study the shape characteristics of these planets as well as how they align with planetary formation and solar system structure. Super-Earths and mini-Neptunes are planets with masses 2 to 10 times that of Earth, with radii ranging between Earth and Neptune. Super-Earth, rocky planets with a radius 1.75 times that of Earth and possessing a relatively thin atmosphere are classified as super-Earths. While planets in the sub-Neptune group typically have radii 1.75 to 3 times that of Earth, they possess dense atmospheres along with smaller rocky cores. However, these definitions are still being refined. Researchers are uncertain whether blood gas is the optimal criterion for distinguishing between the two types, or whether other factors such as species also play a significant role. We all know that super-Earths and asteroids have diverse compositions, ranging from rock, ice, and metal to every intermediate form of matter in between. We know they could have an atmosphere, though whether they contain oceans or underground water sources remains a matter of debate. These captivating worlds appear incredibly rich and diverse. Although scientists have long believed in the existence of exoplanets, it was only in the last 3 decades that technology advanced enough to fulfill humanity's quest for discovery. Since the mid-1990s, astronomers have discovered thousands of exoplanets, including 1,661 classified as super-Earths to date. So how can we recognize them? Several unique methods have emerged. All planets interact with their host star through gravitational force, as both the star and the planets orbit a common center of mass. Some planets interact strongly with each other, which occurs when they have large masses, small distances between them, or a combination of both factors. When a planet orbits its host star, it exerts a gravitational pull that causes the star to wobble slightly, moving alternately closer to and farther from Earth. Scientists refer to this oscillating phenomenon as the star's light shifting toward the blue or red end of the spectrum. This shift is commonly referred to as the radial velocity method. The radial velocity method is particularly effective in detecting hot Jupiters, large-mass planets orbiting their host stars, because they create a stronger resonance in a shorter time compared to smaller and more distant planets. Therefore, this method primarily detects hot Jupiters well but is less effective when searching for super-Earths and mini-Neptunes. Even nearby stars produce smaller signal amplitudes because they have modest masses. Another method to detect planets is by measuring their motion. Astronomers observe a slight dimming of the star as a planet passes in front of it. Scientists can deduce the size of a planet based on the dip in brightness it creates on the light curve or the amount of measurable starlight over time. This method is particularly effective for large planets close to their host stars, as they block more of the star's light when orbiting. This causes a significant decrease in brightness and also increases the likelihood of them passing in front of the host star from our perspective. The necessary condition is that the planet and the star must align directly along our line of sight for the transit phenomenon to be observable. Due to their dependence on orientation, many systems cannot be detected by this method. The planets do not align in a straight line between Earth and their host star, which is the simple reason explaining this. If both methods can be combined, astronomers can determine the size of a planet based on its motion, mass, and radial velocity. This helps us calculate the planet's density, thereby allowing for more accurate predictions about its composition. This could suggest the possibility of life existing there. But what is it about super-Earths that captivates us so much? After all, Earth is the only planet we know of that harbors life. So why don't we focus on exploring and studying smaller planets? Throughout Earth's 4.5 billion years of formation and development, large life forms were absent for most of that time. The activity of the Sun and geological processes have caused significant climate changes on the planet over time. It has become a hospitable place, fostering favorable conditions for life to thrive. But these changes are inevitable, they will come naturally. Super-Earths and asteroids are incredibly fascinating topics, because they can open up better opportunities to create a suitable living environment and attract residents. That's because there are too many red dwarfs in orbit, a type of star with a lifespan much longer than our Sun, extending time to allow conditions to change and life to have a chance to emerge. Red dwarfs vastly outnumber Sun-like stars, differing by several orders of magnitude. and nearly half of the red dwarfs surveyed so far possess super-Earths. Not only do many red dwarfs host super-Earths, but about 50% of them also have super-Earths located in the habitable zone, where the temperature is suitable for liquid water to exist on the surface. In the solar system, this is the region of space located between the orbits of Venus and Mars. Based on those statistics, astronomers estimate the number of potential super-Earths in this region. There could be tens of billions of potentially habitable planets orbiting stars in the Milky Way. Therefore, the exploration of super-Earths and asteroids is incredibly fascinating. To illustrate the process of planetary system formation and evolution, this is also very important due to its potential implications for the search for extraterrestrial life. Not only does it involve exploring new worlds, but studying their characteristics is also crucial in determining whether do they contain favorable conditions for life? The James Webb Space Telescope is the largest and most powerful space telescope ever created by humanity. A portion is dedicated to this mission. The mirror has an area 6 times larger than that of the Hubble Space Telescope. Its devices operate at infrared wavelengths. In addition to 3 cameras, the James Webb Telescope is also equipped with several other scientific instruments. The system includes multiple spectrometers and cameras. The spectrometers function to disperse light into different wavelengths. The passage allows us to explore the temperature and chemical composition of a planet. These rings block unwanted light from the host star, allowing the planet's light to reach the sensor for direct imaging. Thanks to these tools, James Webb can observe the atmospheres of exoplanets in detail. Currently, scientists are able to search for signs of water, methane, oxygen, and other molecules. Provides deep insights into the atmospheres of super-Earths and mini-Neptunes. These observations are opening new avenues in the search for biosignatures, common evidence of past or present life. Although the search began with the James Webb Telescope, it may take both ground-based and space telescopes to complete it. Moreover, it holds even greater significance in helping us truly understand the nature of life's potential existence on such planets. Clearly, super-Earths are not difficult to form, but the key to understanding how these unique planets are created remains a mystery. The answer lies in understanding how all planets are formed. The models show that the planets in our solar system formed through the gradual accumulation of matter in the disk of dust and protoplanetary gas around the young sun. Inside the material disk, regions closer to the center have a higher density of matter, but the area right next to the star contains very little material. Snowline. For example, water in its gaseous state. Outside the runway, the lower temperature causes water and other compounds to exist only in the form of ice. Therefore, the inner part of the protoplanetary disk formed smaller but denser rocky planets, including Mercury, Venus, Earth, and Mars. At the outer edge of the protoplanetary disk, material often accumulates faster and forms larger planets. Their gravitational pull then drew in nearby gases and dense atmospheres, forming planets like Jupiter and Saturn. This is called the core accretion hypothesis, the most widely accepted model for how our solar system formed. To have a super-Earth is due to Jupiter. Its orbit is the primary factor governing the dynamics on the surface of our Sun. Scientists believe Jupiter may have moved into the inner solar system before returning to its current position. This motion will destabilize the orbits of nearby objects, causing a large amount of matter to be pulled toward the Sun. Rentat's hypothesis. But what if a super-Earth existed? Stephen Kent, an astronomer at the University of California, conducted computer simulations to predict the effects of such a planet on our solar system. His experiment involved introducing a fully formed super-Earth into the current solar system and simulating its evolution over 10 million years to observe the results. Studies clearly show that adding a super-Earth to the solar system would severely disrupt the orbital stability of other planets. Although gas giants like Jupiter and Saturn are relatively stable, fluctuations in Jupiter's orbit have pushed one or even all 4 rocky planets farther away from the Sun. In some cases, even Uranus and Neptune can be ejected from the system. Ken realized that reducing the mass and placing the super-Earth 3 astronomical units from the host star was the most stable solution, while also having minimal impact on Jupiter's orbit. Outside of this exact scenario, everything will take a turn for the worse. Although many astronomers long to find this planet, fortunately, it does not exist. In other solar systems with stars similar to our Sun, Jupiter-like planets are rare, while super-Earths are common. Therefore, our solar system may not be the ideal model for constructing a general theory of planetary system formation. As scientists continue to explore exoplanets, they are gradually uncovering some remarkable trends. Specifically, most super-Earths are composed of rock. When multiple super-Earths coexist in a star system, they often exhibit remarkably similar characteristics. For example, in terms of size and mass, there seems to be a certain design principle or pattern governing the formation of super-Earths. But why is that? Once again, it seems the key lies with Jupiter. In 2020, two astronomers, Kostadin Petegin and Alexandro Mobidelli, proposed a new hypothesis about the formation process of Jupiter's 4 largest moons. They are nearly the same size. Like a young sun, Jupiter was also enveloped by a disk of material from the moment it formed. Researchers point out that the balance between the gravitational pull of dust particles toward Jupiter and the force pushing them away forms a ring around the planet. Includes particles of a defined size. These particles are the fundamental building blocks of the moon. They accumulate matter until the centrifugal force within the disk causes them to break away and stop growing. This will repeat over and over, creating many nearly identical bodies. From there, those same researchers developed this theory into the field of planet formation. They observed that in protoplanetary disks, a similar ring-shaped structure forms where matter accumulates as forces reach equilibrium. Their research model indicates that in star systems with multiple rocky planets, when rocky super-Earths reach a certain size, they will move toward the star and stop growing. This process then repeats with the next planet. The research team's latest findings have been published in the journal Nature Astronomy. Although still a nascent theory, this model shows great potential in explaining why our solar system lacks super-Earths. The architecture of the solar system appears to heavily depend on the orbits of its planets. With smaller orbits, we achieve a stable solar system. In the universe, planets are similar to those on our Earth. A larger orbit can create uniform planets, known as super-Earths. The mystery of the missing super-Earths and mini-Neptunes in our solar system remains unsolved to this day. Studying these exoplanets is one of NASA's top priorities, and the James Webb Telescope plays a pivotal role in this mission. This fascinating and challenging field of research has the potential to yield fresh insights into the formation and evolution of planets as well as solar systems. The essential conditions for sustaining life, as well as the diversity and complexity of the universe.